activity, and he told us we are conducting like this. Then I told I had initially given the approval and attend. But afterwards there was some sort of condition, and later the activities were resolved, and thereby I am here before you to present on the Readiness classification on entrepreneurship. Generally, తెలుగులో చెప్పాలి నాకు సినిమా చెప్పారు నేను ట్రై చేస్తాను. అండ్ దట్స్ లైక్ నా స్లైడ్స్ అన్ని ప్రతి ఒక్క స్లైడ్లో తెలుగు ఉంటుంది, ఇంగ్లీష్ రెండు ఉంటాయి. అండ్ ఈ సెషన్కి నేను చెప్పాల్సిందంటే ఒక ఇంట్రడక్షన్ ఉంటుంది, ఒక బ్యాక్గ్రౌండ్ థియరీ ఉంటుంది, దెన్ వాట్ ఆర్ ది మోడల్స్ దట్ వీ కెన్ డూ బై యూజింగ్ క్వాంటమ్ కంప్యూటింగ్ ఆన్ రిడీనెస్ క్లాసిఫికేషన్. అండ్ ఒక పేపర్ తీసుకున్నాను, ఆ పేపర్లో కొన్ని రిజల్ట్స్ ఇచ్చారు. అంత డీటెయిల్ చేయను. ఓన్లీ థింగ్ ఈజ్ ఐ విల్ సీ దట్ ఐ విల్ ఎలాబరేట్ అట్ ది హైయర్ లెవెల్, బికాస్ మీకు అన్ని చెప్తే చాలా డెప్త్ అయిపోతుంది, అంటే మీకు ఏం అర్థం కూడా కాదు. సీ దట్ నేను చాలా ట్రై చేస్తాను మీకు చూడాలి. అండ్ ఆల్సో దేర్ ఆర్ సమ్ అప్లికేషన్స్ ఆర్ దేర్. అండ్ ఇన్ ఫ్యూచర్ ఎందుకంటే ఇంకా టెక్నాలజీ వచ్చి ఇంకా ఎవాల్వింగ్, అండ్ దేర్ బై I cannot say that there is no practical work that is happening, and only one quantum level that is available throughout the world, and it is being connected by different institutions and through cloud, and they are doing the quantum work right now. And it's a evolving technology, and in short, I need to say that in future, at least by as per the plan of India, by 2057, and the IBM may release one quantum computer, and that is one reality that may happen by 2027. And my paper name I have taken from a Switzerland author, and he has proposed some models, and those models that I am going to discuss it. And మొత్తానికి ఈ టాక్ నేను ఒక 30-40 minutes చెప్పిన తర్వాత మీరు ఏమి వాట్ యువర్ గోయింగ్ టు టేక్ అవే. అండ్ ద ఫస్ట్ థింగ్ ఈజ్ ఒక 2 మోడల్స్ ఉన్నాయి. ఒకటి మోడల్ వచ్చేసి హైబ్రిడ్ క్వాంటమ్ న్యూరల్ నెట్వర్క్, అండ్ ద సెకండ్ మోడల్ ఈజ్ మీరు సిఎన్ఎన్లో కానీ డీప్ లెర్నింగ్లో కన్వల్యూషన్ నెట్వర్క్ ఉంటారు. ఇక్కడ క్వాన్ కన్వల్యూషన్ నెట్వర్క్ అనేది మోడల్ ఉంది. అండ్ వన్ మోర్ థింగ్ దట్ ఐ కెన్ సే ఈజ్ క్వాంటంలో మనం ఏమైనా అప్లికేషన్ చేసామనుకుంటే ఇమేజ్, అండ్ సిన్స్ మన క్యూబిట్స్ ఉన్నాయి కదా, క్యూబిట్స్ ఇంకా నాయిస్ ప్రొడ్యూస్ చేస్తుంది. అందుకోసమే ఐఎమ్ సేయింగ్ దట్ ద స్కేల్స్ ఆఫ్ క్వాంటమ్ వేర్ నాయిస్, అండ్ దట్ ఈస్ వన్ థింగ్ that is happening when I apply for the image classification neural computer. That is ఎందుకు అది మన మొబైల్ ఫోన్స్ ఉన్నాయి, మీకు చాలా ప్రాసెస్ ఇమేజ్ బై యూజింగ్ వేరియస్ యాప్స్ ఆర్ దేర్ టు క్లాసిఫై విత్ డిఫరెంట్ మీన్స్. బట్ ఏమవుతుంది అంటే ఫస్ట్ ఆఫ్ ఆల్ every day some trillions of images are being developed. Every day trillions of, that's why what I'm saying is the data explosion in the computer vision, and we can say that there are going to be many high resolutions that are being generated nowadays, because as the technology got improved, and thereby many high resolutions that are being generated, and similarly we are using an app, we are generating data through different apps, not only UPI and saying, and through different apps, and we are generating the data, and thereby the data is going to become a large amount, and thereby in future the processing will become difficult. And the second thing is already computers live on us. We have the computers and we have the deep learning models also, and with the help of the graphical processing units and memory, all distributed systems, all these things ఉన్నాయి. But ఏమవుతుందంటే కాస్ట్ ఎఫెక్టివ్ చాలా అయిపోతుంది. Thereby we need to say that this is also one of the things that we have to consider the quantum computing. మీరు రోజు క్లాస్కి వస్తున్నారు, ఏదో రొటీన్గా ఇంటికి వస్తుంది, కాలేజ్కి వస్తున్నారు అని చేస్తున్నారు. ఏమైతే ఉంది, ఇట్స్ నథింగ్ బట్ you are doing the same activity, morning 9 class, 8 class, college. But the thing that the current computers are also doing the same. And thereby, if I do all these things, they are solely memorizing science data. And suppose I go to call out a plan, if I say that thing, and thereby it is going to be not going to do such type of activity, thereby I need to say that it is going to memorize science data instead of generalizing, and thereby overfitting is going to happen. And thereby, this is one of the important things that we have to consider in the English classification. Why quantum? And the first thing is parallelism. For suppose a deck of cards ఉన్నాయి, 52 or 54 cards ఉన్నాయి. దాంట్లో ఒక కింగ్ కార్డ్ తీయాలి అంటే మనం ఏం చేయాలి? We have to take card by card, and thereby after certain cards we are going to read it. Whereas if I apply my quantum computing, definitely the system, the quantum computer will scan all the 54 cards at a time, which is going to pick that particular card. And thereby the quantum parallelism is going to provide a lot. That's why what I am saying is it is going to process exponentially many dimensions simultaneously and extracting the rich features. And the second thing is speeding up. And right now there are many quantum algorithms are there, and those algorithms they are giving some information and at some particular level only. And with those things, and if I include general whatever the classical optimization algorithms introduced yesterday, so that I can improve the speed up on machine learning, and I can get a better interference. And similarly, you can handle the high damage. So far, I told you one example, the deck of 54 cards. Suppose a maze from starting to ending చేయాలి అని ఎండ్కి వెళ్ళాలి అంటే ఫస్ట్ మీరు ఒక ఫ్రెండ్ వెళ్తాడు, యూ కమ్ బ్యాక్ అండ్ ఆల్ ఆఫ్ యూ అగైన్ కమ్ టు స్టార్టింగ్ పాయింట్. Likewise, you people are going to rotate one by one. These are only thing is all people, because all people will go at a time, and one can come out from start and at one point. And thereby, I need to say that it is going to have the effective dynamic. And the second thing that I can say is, since we are taking help of the classical machine learning concept, and thereby I need to say that we need the deep learning also, because the US classification clearly nowadays we are going for a deep learning, and because of many other use cases, and thereby you only limitations. First of all, you see any convolutional network, and with the person program, everything is going to have the convolution layer, pooling layer, and each layer we have different number of ways. At one time, one layers thereby the number of very vectors we have to try is going to be very difficult, and thereby we need millions of parameters, and thereby in training it is going to lose, it is going to need the many computational resources, and it will take a lot of time. It is a current convolution problem. And similarly, మనకు కావాల్సింది నెక్స్ట్ ఇంటెన్సివ్ కంప్యూటేషన్. అండ్ ఈవెన్ దో మనకున్నా కూడా గ్రాఫికల్ ప్రాసెసింగ్ యూనిట్స్ కానీ సెన్సార్ ప్రాసెసింగ్ యూనిట్స్ ఉన్నా కూడా దే ఆర్ ఆల్సో నాట్ గోయింగ్ టు డూ, బికాస్ ఇట్ ఇస్ గోయింగ్ టు లీడ్ హై పవర్ కన్జంప్షన్ అండ్ రైజింగ్ సస్టైనబిలిటీ. అండ్ సిమిలర్లీ ఇవన్నీ not on a platform, because everything to be transported on a edge device. It may be mobile phone or it may be camera, whatever it may be. You only being transferred here, it is also becoming very difficult task. And thereby, I need to say that this is one of the bottlenecks if at all I want to make on the edge devices by using the deep learning. And because of three reasons: one is the limited memory, and the next point is the processing, and also the latency. Because when the latency kavalante, suppose if I am speaking right now, and it should be immediately, you should be in a position to view it within 1 or 2 seconds. After maybe 1 hour, if I am able to read it, then obviously it's a waste of time, and that's why we have to avoid the latency requirements also. ఇంతవరకు ఒక సినిమా స్టోరీ మాది ఉంది. Now we'll go for, because already in the quantum computing basics. I don't want to go inside those basics, and the only thing is I touch upon the basics. And first of all, qubit states. So when you see the qubits, and thereby I mean to say that in the qubit state, and you are aware that in the 67 systems law, qubits and thereby the qubit state 0 and the qubit state 1. Just like digital logic 0 and 1 equal, we have the qubit state 0 and 1. And we have one more thing called as the superposition. And ఈ superposition ఏ విధంగా వచ్చిందంటే ఈ block sphere representation లో, and thereby that will provide you the superposition concept process. And ఇది చెప్పాలి అంటే I can take 1 hour class, because between these two things, qubit and the block sphere representation, if at all I want to deliver a talk, I can deliver for 30 to 45 minutes. Why the sense? The mathematical concept is there, even though I'm not going into those details. And the second thing is, the block sphere it is going to do a state, and thereby with the properties we have to use the alpha square or beta square. Here a classical example and the toss racer అనుకోండి, or if you take a coin, if you flip it, then obviously it should be head or tail. And that is the best example of block sphere. And it is going to have both either head or tail or padali. A padali, the probabilities compulsory, thereby we are going for the probabilities in terms of alpha and beta. And okay, it is into okay, it is. And digital logic lo manam 1 bit ante 1 is nothing but 0 and 1 order. And whereas here also we are going to go for the same way, but we say in terms of the basis task. And thereby 1 qubit is represented by okay. So 1 qubit 0 and we are representing it by the column vector 1 0, and if the 1 qubit is there, we are representing it by 0 and 1. And ఈ representation different people will use differently. ఒక bracket అంటారు, ఒక qubit అంటారు, ఒక ket అంటారు. ఈ విధంగా different people will call differently. And final గా ఏం ఇన్ఫర్మేషన్ తెలుస్తుంది, ఒక 0 ని ఏ విధంగా క్వాంటం రిప్రజెంట్ చేయొచ్చు, and 1 ని ఏ విధంగా క్వాంటం రిప్రజెంట్ చేయొచ్చు, and that we are doing in the form of a 1 column vector. And suppose if at all I have 2 qubits, or digital logic law 2 bit information unte, how we are going to represent 0 0 is nothing but 0, 0 1 is nothing but 1, and 1 0 is nothing but 2, and 1 1 is nothing but 3. And ikkada kuda 2 qubits unte the same thing that we are doing, and we are going for 0 0 qubit, and where we are going to do the inner cross product or the Hilbert cross product, and 0 0 0 1 and 1 0 and 1 1, and the basis vector వచ్చేసి inner product చేసినప్పుడు, and I'll take the left one, and I'll take the second column 1 0, and thereby I have 1 0, and I'll take the second row and the first one 0 into 1 like that, 0 into 0, and thereby I'm representing it by 1 0. And in that way I'm going to represent 0 0 by this basis vector, and similarly 0 1 and 1 0 and 1 1, and we are representing the right column that is here, that is being represented, and in that way we can extend for n number of qubits. When you see the thing, and we are getting a entire diagonal elements are going to get 0, and if we are going for representing a 3 by 3 qubits, then I am going to get 9 states, and thereby I am going to become a diagonal. And దీనికి కావాల్సింది ఏంటి అంటే, but we are saying that image classification, and thereby one thing that we should know is how we are going to represent an image in quantum technology. If the left side though, that is figure A is nothing but a classical image, and the base I am showing 4 pixels, and the 4 pixels having intensity 0 and 125, 200 and 255. As I exhibited the representation of those, then obviously the figure B I am going to represent it. And if at all I want that model not having some disadvantages, and thereby they want for one more model, that is FRQI. Then afterwards they want for OQI and NEQR. And in that way, we can represent any image in quantum computing multiple ways. It is nothing but people feel it is an evolving thing. It is standard and separate. Just we have an image we can represent between 0, 1, or it depends on number of bits that we have, and it is separate label. But still it is in the process. And in that way, we can get the quantum wave difference. With nothing standard so far, not standard, and thereby we can take any of the representations. And next, why I am showing all these things? Now, finally, the model model requirements I am saying 2 models already. Our 2 models requirements, they need what we have to take, and in that way, I am going to all these things. And similarly, in the case of digital logic, we have NOT gate is there, AND gate is there, OR gate is there, the universal gates are NOT and AND, and likewise we have the gates. Here also, I can go for different types of gates called AGMAT gate, X gate, Y gate, Z gate, and similarly I can go for the rotational gates also. And similarly, if I have multiple inputs are there, I can go for the controlled NOT gate, or I can go for the controlled Z gate. We have to build a quantum circuit, and for that quantum circuit, I need all this information. Why in the sense, in my model, I am going to build a quantum circuit, and that quantum circuit is depending on these basics, and thereby we need this quantum circuit, and where it is going to manipulate the information of the respective image, and what we are going to do in the case of generally if I design a counter, how if I design a counter and how the states are going to change. Here also, my pixels are changed. And overview case to oriented, and this is an identity gate, and similarly this is nothing but X gate, and this is nothing but a NOT gate, and similarly we have Y gate, and similarly we have a Z gate. Only difference is in terms of the phase of the quantum bit, we call it as the Y gate, and if I go for the phase of only 1 bit information, then I can go for the phase gate, and where the controlled gate is represented on the right side. Because learning is until unless you work it out, then you will come. Otherwise, it is a very, very big. Then you only chase the one thing. One thing is, I told you already, parallelism kavali. Parallelism kavali ante, then obviously the 2 important terms that every quantum engineer should know is, one is the superposition, and the second thing is the entanglement. This is compulsory. And superposition because the quantum bits are there 0 and 1, because in the digital logic they are guaranteed. Whereas if I flip a coin, that coin may turn out to be head or tail, it depends on the probability, and thereby I am saying that in the quantum computing, if at all you are going for it, these 2 terms are very important. One is the superposition theorem, and the second one is the entanglement. Entanglement I cannot, because suppose if the professor is there, and if he is coming to the class, and it cannot be there somewhere else, because there are many examples that I can use for the entanglement, and thereby if I make it within 100 meters, that should be same. If I go for 100 kilometers, that should be same. If I travel on the moon also, that should be same. And thereby, in quantum computing law, the entanglement, there is going to be no change, there is a lot of correlation between the things what is happening. And these are the fundamental difference. In concept ఏంటి? First of all, quantum machine learning తెలుసుకోవాలి. then we will come for the quantum machine learning, how we are going to apply it for the image classification. And quantum machine learning concept and we are integrating the general machine learning, we are integrating the machine learning with the quantum computing. Because there is nothing we can do, but only thing is we are merging the quantum computing and the machine learning. And one more thing that what we are doing, we are going to develop the quantum circuit. Because already given some examples, and we are going to develop the quantum circuit for different types of process. And for that purpose, I need, because when you see a CNN, I need some layers. Here also, I need a quantum layer. It is going to be bit time, and thereby I am going for the learnable layers or the quantum circuits. The quantum circuits layer the gates ఉంటాయి, rotation gates ఉంటాయి, XYZ gate and the control gate, key gate, all these things are there as part of the training, and one use for optimization purpose. And once I have the quantum circuits that I am going to develop, then we are going to extract some features from those circuits. That is very important as part of image classification, and thereby I am going to go for the extract the features by using those quantum circuits. And features అంటే for suppose the mobile phone the TV screen ఉంటుంది. ఈ screen కి features ఏమున్నాయి? ఒక 4 ఎడ్జ్లు ఉన్నాయి. And similarly background ఒకటి ఉంది. And similarly ఒక blue color podium ఉంది. ఇవన్నీ features ఉన్నాయి. So suppose if I can describe any features for any, and that's why the quantum circuits are going to define all these features. And the second part is, then I is going to be endless. I have to optimize and for my training also, and thereby I am going to apply the general optimization algorithms. That's what we are going to use in the machine learning, and thereby people are going to preferring the gradient descent algorithm, and the second one is Adam algorithm, because the machine learning idea will take in the batch propagation. We are during the training phase, we are going to use the gradient descent algorithm, and thereby the algorithm is work. And similarly, advantage ఏంటి అంటే మనకి ఏం కావాలి, any complex high dimension features may be in accessibility and classically. And in the further extend చేసుకుంటూ పోతే ఈ దీంట్లోనే then we can go for the parameterized quantum circuits, and we are going to train these things at the layers also. Because as we are doing in the case of the machine learning or the deep learning, we need some training part, and with quantum circuits we are going to train. And similarly, in doing so, we have to use the optimizers, and similarly, this is going to be a continuous process, and thereby we are going to do in a loop. At one instant, I cannot make the people to completely train the model for that thing, and in that way, I am going for it. And finally, it is going to leverage the quantum expressivity, and it is going to provide the classification layer. In that way, this is my quantum machine learning concept. And ఇవన్నీ చేయాలి అంటే again I need to apply some basic math, what I know about this computing, because I am not going to go into details. Only thing is I may have to go for encoding by using the quantum bits each pixel, and similarly ఒక్కొక్కసారి pixel value exceed అయిపోతే then it is going difficult to process. What we are going to do, we are going to normalize that pixel also, and thereby the normalization we are going to do. And depending on, because if at all I want to express a pixel with 16 bits, then what I do is I reduce these things, and thereby I am going to go for fewer bits also. And in that way, I have to do a lot of practicality in doing this. And the extension is whatever I told you, we చేసిన మనకు లాభం ఏంటి అంటే, and we are going to classical data into high dimension spacing, because I have a size of image around some 10,000 by 10,000. The size of image is there. Then if at all I want to process by using this thing, then it is very difficult, and thereby I have to do something. And if I do some sort of mapping, then I can do a lot by using similarly, we are going to have the linear separability because machine learning law, one of the important things that what we speak is image 0 now 1 na we are going to draw a line and thereby we are saying that if we put all the there, then we have to go for the linear separability and by exploiting the quantum properties and we can represent the and idanతా machine learning because adanతా రావాల్సిన first model ki second model వచ్చేటప్పుడు I need the quantum convolution network or what I mean to say convolution neural network. This is the second part of the model what I am proposing and here also I need because instead of going for the convolution filters or the flowing filters, what I do is I go for the quantum circuits and they are going to identify some features and thereby I need we are replacing the Siemens convolution with the quantum filters and we are going to patch the quantum circuit for these features. Then finally we are going to have a layer where it is going to extract the features and where we can do some sort of image classification. Image నేను రెండు మోడల్స్ చెప్పాను ఆ మోడల్లో the first part was very clear and the second part is now. We'll see the first part of it. It's very simple because I'm not going in depth of the thing and what I do is as I told you I need the quantum for the quantum circuits and దానికి ఏం చేస్తానంటే my image I make it to small pieces of 2 by 2 or 4 by 4 something like that depends on my requirement and thereby I will group into features then I will develop the quantum circuit then each circuit is going to identify one feature. Suppose ఒక సర్క్యూట్ వచ్చేసి ఓన్లీ రైట్ సైడ్ ఎడ్జ్ డిటెక్ట్ చేస్తుంది ఇంకో సర్క్యూట్ వచ్చేసి లెఫ్ట్ సైడ్ ఎడ్జ్ డిటెక్ట్ చేస్తుంది ఇంకో సర్క్యూట్ వచ్చేసి బాటమ్ ఎడ్జ్ డిటెక్ట్ చేస్తుంది. Likewise, I am going to make many quantum circuits for the features. In this case, I told you only 4, but you can go for multiple options for my image. Then afterwards, what we do is we are going to merge because only merge here. When merge is application of then obviously I have to merge all these classifications. Then in doing so, I have to exploit the quantum parallelism also. And this is the main idea, the hybrid model, what we are saying. And our model, what we are doing is the parallel circuit design, and the first part is each circuit is going to have a subset of features. The circuit left, right, that is going to do all these things, and also it is going to exhibit the parallel feature extraction into multiple circuits. And suppose ఈ సర్క్యూట్స్ చేసినప్పుడు ఏమవుతుందంటే మనకి ఇంకా టెక్నాలజీ ఇవాల్వ్ అవ్వాలి కాబట్టి ఈ సర్క్యూట్స్ దే మే ప్రొవైడ్ సమ్ నాయిస్ ఆల్సో because when I say that if I see digital logic it is going to provide a definite information whereas here still it is evolving and thereby it may provide some noise also and thereby I have to see that these circuits should provide reduced decoherence because whatever the thing that is going to do for that purpose and there are many ways we can make it and we'll see that while developing things and we have to consider these things one is the gate depth and we need devices where this noise to be get reduced and also similarly hardware key, software key we have to compromise on all these. And the second thing, this was my basic flow, whatever I told you. And when you go in depth at the next level, and this is the flow that what is being done. For image classification, we are going to do the image pre-processing. For image processing, then the image processing is mandatory here also. And the second part is once I have done the image pre-processing, then I have to identify the features by using the quantum circuits and afterwards I have to go for the parallelization of these two circuits and once I got it then I can go for the classical aggregation and the classification and that we are going to do some sort of manipulation I have created some fundamentals, and with those things that we are going to do. And the final output that you see, this is my final class lecture. And this is about the final this is my simple convolution what we are doing. With the help of, because I want to classify the image, what we are doing is my image input image of size 28 by 28. Then afterwards we are doing the convolution. Then afterwards we are doing the pooling. And likewise, these layers are repeated in the general deep learning things what we are doing now. These layers also we are going to add the quantum circuits we are going to add at the next level. In between the convolution layer and the flattening, we are going to add one quantum circuit layer. Likewise, we'll add one quantum circuit layer, and afterwards we are going to flatten, and afterwards we are going to go for the software function for identification, because these are all algorithms, and thereby I am saying even though I am saying software function, but the input number set to type, but it has to show only, you are going to throw many probabilities. In that probability you will take only one thing, and thereby in that way the final architecture, that is the model one, we have this model wherein the machine learning is there, the deep learning is there, then followed by the quantum circuit, followed by the flattening, and followed by the classification. And final efficiency emotionally, if I use a basic CNN, and I told you the number of bits per hour, ఇక్కడ 80,000 values వస్తే ఇక్కడ వచ్చే is going to become 10,000. And how we got it, all these things, we have some calculations are there. And if you are interested, then I'll tell you the paper title. And only thing is, if you go through 3 or 4 times, definitely you get all these things. There's nothing like new and new. And one thing is, in doing so, first of all, taking the all then we are going to use a take of the atom optimizer for training purpose. You can go for the gradient digits also. Whereas in this paper, they have taken the atom optimizer, and similarly, the loss function is also required as part of the deep learning. Here also they have taken the loss function, and the loss function to the cross entropy. And data size, what they have done is 70% is for training, and 15% is they are taken for validation, and 15% is for the testing of the data. And to ensure that to prevent overfitting, in that way they are assumed some conditions, because if you know something about machine learning, and definitely you will understand all these terms whatever I am saying. And in that way I will go for, and finally this is the model 1 circuit that has been designed, because when you see the left part of it is nothing but a simple CNN. Then after the max pooling, and they have designed the quantum layer, and this quantum layer is built with the quantum circuits, that is the fundamental qubits, and also the gates, what are the quantum gates they are there, and it is going to be a layer. Then afterwards they are getting flattened, because it has part of deep learning. Automatically the next layer is flattening layer. Then obviously the last layer is the output layer, and the way it is going to grow by using software function will grow all the 0 to 9, and it is going to show some information of this which is having the highest probability. We have to consider that thing as a question. And in that way, the respective quantum circuit, and we have done this thing. And this figure I have taken from the famous authors, because they are the first people they developed, and I have taken this figure from this paper. And the second model because we have taken only the quantum circuit, now we will go for the convolution layer. As we have seen that convolution layer, and here we are going for the convolution layer. And here also, because we are going to take a layer, because what we do is we have to take a quantum kernel, and which is going to process various images. Because we have some techniques are there, how to split it, there are some conditions are there, and that I am not saying all these things. And finally, the convolution layer is this will have to provide some future maps. it has provided some feature maps. And also, when you see these things, and it is then passed on to the classical dense layers, there is a respective this thing, and it is going to flatten the quantum features, and afterwards it is going to learn higher representation of the classical probabilities. And ఇక్కడ ఏ విధంగా పనిచేస్తుంది అంటే we are going to go for this sliding because image ఉంది అంటే obviously because in the earlier thing what we done is we split the image. Whereas ultra we have to go, we have to rotate, we have to slide from top to bottom, right, left to right, then again left to right. Likewise we will show in a process, and thereby we are going to generate the quantum circuit input. And once I have done the thing, then information, whatever the input that they are doing, we are going to make into qubits. And afterwards, we are going to go for the quantum circuit. Quantum circuit, that is the parameterized quantum circuit. And by using the C0. In the earlier case, we are not using the C0 gate, whereas here we are going to use the C0 gate. And in that way, that we are going to go for it. And finally, it is going to yield some classical values. And in other words, these classical values will act as a convolution layer and support the quantum operators. And this is the, and efficiency question it is taking some nearly 40,000 Siemens parameters, and it is going to take a QN parameter of 10,000. And we will see the features of fewer parameters will come down to 4x, and it is going to have, because in the intermediate graph it is going to have 10,000 parameters for the 4,000 parameters, and this I don't want to discuss. And this is my final convolution quantum network. I mean, the convolution bubble. We are seeing the deep learning layer followed by the quantum circuit, whereas now in the initial stage we are taking the convolution layer, then afterwards we are going to do the feature mapping, then we are going to flattening, then afterwards the how to play with it. In that way, that the second network or second model is being developed. And this is also not a simple thing. If you make one or two times with the fundamental system, it is very easy to understand also. I am able to express so freely in the sense because I already work on something, and thereby I am able to deliver, I am able to speak to you by using those persons. Because there is nothing like, because studying is evolving. Because we can take the help of the MATLAB and we can implement it also. But we are getting it, but for that there is no validation. Because my student is doing one of the work on quantum computers only because of the convolution layer. And because we have done a simulation, but there is no guarantee that simulation is correct or not so far. Why? In the sense we don't have any quantum computing so far. But the only thing is we are assuming that it is there, and because there are many tools are there. We are not limited to MATLAB only. We have many tools are there online, and so that we can simulate all these networks by using either quantum circuits or quantum convolution layers, and there is no end for it. Because if you browse or if you Google it, we will get number of Python programs for each and every case. There is no limitation at all. Everyone final idea is they are going to achieve the classification or how to make the quantum circuit or how to make the convolution. And the programs are not so lengthy. Only thing is they are going to take multiple things in their Python code. If you go to GitHub, then GitHub will provide nearly more than 10,000 Python codes for these quantum computing areas. Whatever I told you, quantum circuit or convolution layer, and there are many things like that. And this also I have taken from the same author, and thereby because they have developed and they have also worked on the quantum computer because they have access to it, and thereby and finally they have given the network in this fashion. And similarly, and then anything that we are doing, what are the technical conditions that we are doing while developing because we have taken many conditions are there and I'm giving only a general condition. I am not going to go for a specifically you have to do this thing. But these are all some general conditions. For suppose we have a circuit design testing we should know the information about what is the operational diode, what is the operational transistor. Here also, when testing we have to consider some technical part of it. And we'll see that the number of qubits per circuit we are going to be taking 2 by 2 only because still we don't have a evolved technology go for 3 by 3 or 4 by 4 something like that. And thereby, because at the present conditions they are limiting only with 4 qubits only because that's the thing. And similarly, the circuit depth they are not going in depth. When you see the previous figures, and we are taking the levels are only 3 or 4 levels only. Whereas if you go for the thing, I can go for more number of depth that is not being done so far, and they are considering only 3 to 4 levels of depth, and they are considering 2 to 4 layers of the qubit rotations, not going for more than those rotations because of the limitations of the computations. And even though the GPU TPU it is difficult for us to make all these things, and thereby it is one of the things. And similarly, the connectivity is very, very important, and in doing so, we have to consider the C0 gate and C gate and for these things. And similarly, the entanglement is very, very important. I told you that the superposition and entanglement, and these things are to be considered. And definitely, whenever we are doing something, we have to compromise on something, and thereby there are some design trade-offs are there. And if you go for more qubits, we can achieve the rich futures with higher noise. Whether you need lower noise, then take the less number of qubits, and so that you can achieve the things. And in that way, there is a compromise so far. There is nothing like saying that this is not guaranteed or this or that, because it's the area of development. And similarly, the circuits, whatever we are doing for it, we are not going for 3 or 4 levels only. We are limiting only to 3 or 4 levels only. And that's why many of you know real world simulation ki real time quantum hardware ki చాలా difference ఉంది. And thereby because simulation చేసినప్పుడు we are going to have the noise free environment. So we are doing only the either MATLAB tool or some tools, some Python tool or these things, but this is going to be a noise free environment. Whereas in the case of quantum, I told you already noise is there, and thereby I have to consider and limitations of the simulation is it is completely expensive if you go for more than 30 qubits. This is also one of the conditions that what we need. And similarly, quantum circuits what is noise and gate identity and coherence. You have to consider all this. And similarly, the performance gap is there on the hardware. And real devices suffer from limited qubit connectivity and short coherence times, and thereby the variation circuits we have to consider, and so that we have to avoid noise. And the future outlook of there are many devices are there, and there are devices where we have to see that devices should take the case of the noise also. That is NICT devices. That is one of the important things. That in the future outlook we are going to get these types of devices. Nowadays we have mobile phones, and in those words the technology getting added, and there is a less data that can go. And similarly, because in order to avoid the noise and noise migration and migration strategies, we have many strategies are there, and there are many limitations are there, and I'm studying only a few. And so far we have spoken about the quantum computing, how we can apply, how we can play, and what optimization that we can go to. But so far, no one has gone for what is the quantum error. That is also one of the important things that we consider, and thereby this is one of the limitations currently. No one is taking care of quantum error. What is going to be? That is one of the things that we have to consider. And there are many approaches in doing the quantum circuits, and especially we have to see about the short and shallow circuits, and noise optimization, and error mitigation techniques, and also we need the hybrid processing also. And here also we have to go for the compromise, and whether I need that thing, whether I need this thing, then obviously there is going to be a lot of trade-off that is going to be there in doing so. We'll see some applications, and I have shown you 3 applications. One is the autonomous systems, and one is the security systems. And the PDF file is PDF file is applications. Okay. And there are some applications have been developed so far. One is the medical application, and where we can identify some anomaly in the tumors, that is MRI and CT scan. And so far we are doing with the regular classical computing. And this is also one of the important applications that we have to take care in doing through the quantum computing. And the second application is nowadays we're getting many important things that are happening on our mobile phone, that is security. And the quantum computing is going to do all these things, and thereby there is also one of the applications that what we can next slide. And similarly, nowadays we have driverless cars are there, unmanned aerial vehicles are there, and in all these cases, we have to see real-time detection, and it has taken its own operations. And this is also one of the important things that we have to consider. In considering, I'm saying that what are the benefits that we are going to have, what are the limitations that we are going to have in all these applications, whatever I stated, and I'm not going through those statements, I'm simply giving the applications, whatever we have. Next. And finally, my main GCM, I told you 2 models, and these 2 models, and what is that I that have been taken care. And when you see the first model, that is by using the parallel computing circuit, and they have tested on the NNet database. NNet database అంటే మీరు సంతకాలు చేస్తున్నారు, బ్యాంక్ వెళ్తారు, మీ సిగ్నేచర్ ఉంది, మీ సిగ్నేచర్లో యూఆర్ రైటింగ్ సంథింగ్ దట్ ఈస్ టు బి టాలీడ్. And that is one of the best examples of the NNet database, and thereby they tested on the NNet database, and it is found that 99% accuracy. And when you see along with the accuracy, and the weights also being reduced by 8 times. And also when you see on the medical images, and it is showing some 99% accuracy. And when I consider the cipher data as part of my security application, it is also achieved some 99% accuracy, and when compared to the classical applications. And overall, the nature of similarly, if you go for the convolution network, and they have taken only the 4x feature weight vectors as part of the thing, and they have achieved 67% accuracy. These authors, I am not saying myself, these authors have achieved 67% accuracy. And similarly, the classical parameters, and they have only 53% accuracy. And when you compare the performance with respect to the classical computing models, and it is going to outperform those things, and it will achieve some performance. And similarly, only one thing that is the thing is the quantum training is taking a lot of time when compared to the classical computing, and that is also one of the things that what they have observed. And similarly, there are equivalently quantum simulators are there, and there are many practical applications are there, and likewise these are. And the outcomes I told you. Finally, we have come across some hybrid architecture, and how we are going to reduce the parameters, and what is the impact on different application areas. And these are the 3 things that we come across in my discussion. Yeah. Yes. We'll come for the conclusion. Only one or two slides are there. And the conclusion is, I told you there are some limitations are there. And these are the three limitations I am saying it broadly. One is the noise that is being generated by the quantum hardware that we will consider. And the second thing is, while encoding the information from one domain to other domain, then definitely the encoding is also very, very important, and thereby it may create some sort of bottleneck for the quantum computing. And right now we are only using only 2 or 3 qubits only. We are not going for more than 2 or 3 qubits, and that's why the scalability is not possible. Suppose if I apply my quantum computing on machine learning for this thing, it cannot be generalized for the other cases. That is one of the things that I can say that. And I told you already, simulation is not equal to the real hardware performance. So these are the limitations what the authors they have observed. Yes, with this, so many is my final saying is today's my half an hour or 40 minutes whatever I delivered, and only two things that you have to observe, you have to remember is one is there are quantum circuits are there. And the second thing is the non-convolution networks are there. And how they are being developed, and they are being developed based on the qubits, and based on the quantum gates, and based on the quantum circuits, all these things are being developed. And also one more thing is quantum image. And I told you the quantum image not being evolved so far, there is no standardization happening. And that is one of the important things that what we should consider. And in that way, I need to say that this quantum computing using image classification may be an area where people can do some research right now. And there are one of my scholars doing the thing. But we will see, because I have to started the research last year only. And still we are going through IIT Bombay and IIT Kharagpur also there, and we have my own faculty are there who are expertise in quantum physics. And with the help of those people, we may develop one good research article or research thesis. And after 3 to 4 years, right now it's not possible to complete it because still it's evolving. And in that way, I can say. Now, any questions are there? Any? Then I am ready to answer. There are nearly 60 to 70 are there. Yes, it is not a big rocket science. Only if you focus CSR, then obviously you can get it. Okay. Then my special thanks to Siddhartha, Professor of Technology and Science, and also the AICTE for providing me, and my scholar, my first scholar, and Srinivas, and he known to me right from 2005 onwards, 8 onwards, and 8 onwards he was known to me, and he's been continuously interacting with me, and he has done a good research, because especially he has done on the case of the image classification, and he has done a good research. At that time, it was a good research. Then afterwards, many evaluations have been done, and that was done again, because I have delivered on his it's only at least 4 to 5 lectures at different other lectures, and because only thing is I know something and he has done something. I have learned from him, and thereafter it delivered published very good paper. And in that way, I thank the management of Siddhartha and Atal and Srinivas for giving me the opportunity. And I thank you all, and I wish you all the best for the rest of the year. Thank you.
Thank you, sir. Thank you so much. Thank you, sir. Thank you for your insightful and thoughtful address on the trending topic on the quantum computing. It's a quantum machine learning for image classification. Your plans to receive thank you for this especially. I'm the first candidate under him as a PhD scholar. Under him, sir, 18 members PhD is awarded 2018 onwards. I registered under him as a PhD scholar in 2012. 17 I submitted my thesis, 18 got awarded my PhD otherwise. Like my father, he is a father of me. Right now I'm eating the foods and I listen to this management sir because of this sir. And I worked before this PhD scholar as a faculty under him as a HOD. And when he is a principal, that time also I worked under him as a faculty of under him as an institution. Then luckily I got a full-time scholar in the Rhythm Vizag. Fortunately, I didn't get a stipend. Then I converted it to part-time. Luckily, I got as a scholar under him as a HOD in the Gita University. Right now, sir is the Deputy Director of Accreditation and Ranking. Thank you, sir. Thank you for giving this place for under him as a scholar. Still, I feel as a sir guru, and I will take very interest in this sir. Thank you, sir. Thank you, sir. Coming to the token of appreciation, may I request Dr. Srinivas Baji, Dean instead distinguished resource person, Dr. K. Manunacharya sir, Professor and Deputy Director, Accreditation and Ranking, Gita University. Small token of appreciation, sir.
Safari.